Wormholes, often described as shortcuts through the fabric of space-time, are fascinating structures that arise from the equations of general relativity proposed by Albert Einstein. They are theoretical passages that could connect two separate points in the universe, potentially allowing for faster than light travel between distant regions. Imagine a tunnel with one end placed in a remote corner of the universe and the other in our own solar system. This concept, while still speculative, raises numerous intriguing questions about the nature of our universe and how we perceive time and space. The idea of wormholes leads us to ponder whether they could serve as gateways for time travel. If one could stabilize a wormhole, a person might enter one end and emerge at a different time and place, essentially bypassing the usual constraints of light speed. However, the stability of a wormhole presents challenges, as they are thought to require exotic matter with negative energy density to keep them open. This exotic matter is purely theoretical at this point, as no one has ever observed it. Moreover, the implications of time travel through wormholes are profound. If we could travel back in time, would we alter history? Some theorists suggest that such changes could create paradoxes, like the famous grandfather paradox, where a time traveler might prevent their own existence. Others propose that alternate timelines could branch off, allowing for a multiverse scenario where every possibility exists simultaneously. Moreover, the traversal of a wormhole may not be instantaneous, as one could experience time differently depending on the gravitational fields involved. This leads to the question of time dilation, a phenomenon where time moves slower in stronger gravitational fields, as described by Einstein's theory of relativity. So what if you could travel through a wormhole and experience only a few moments while years or even centuries pass in the outside universe? The mathematics behind wormholes is complex, involving intricate geometry and topology, which can be difficult to visualize. Some models suggest that wormholes may exist in higher dimensions, adding another layer of complexity to our understanding of space-time. This notion invites speculation about the nature of the universe itself and whether there are dimensions beyond our perception. Furthermore, the search for evidence of wormholes is ongoing, as scientists explore the cosmos for signs of these elusive structures. Gravitational waves, ripples in space-time caused by massive cosmic events, are being studied to understand better the dynamics of the universe and whether they might provide clues to the existence of wormholes. As a wormhole in the realm of theoretical physics is a fascinating concept that describes a hypothetical tunnel-like structure in the fabric of space-time, connecting two separate points in the universe or even different universes altogether. It is based on the solutions to Einstein's field equations in general relativity, which allow for the possibility of such shortcuts through space-time. Essentially, you can think of a wormhole as a bridge or a portal that could, in theory, allow matter or information to travel between distant locations much faster than the speed of light would allow in normal space travel. The most commonly discussed type of wormhole is the Einstein-Rosen bridge, which was first proposed by Albert Einstein and his colleague Nathan Rosen in 1935. They were exploring the implications of general relativity, and they suggested that if black holes exist, then there could also be these connections or bridges that link the inside of one black hole to another, potentially allowing for travel between them. However, while this concept is intriguing, it raises a host of questions about stability and practicality, as these wormholes would likely collapse quickly unless held open by some form of exotic matter which has negative energy density. The idea of wormholes has captured the imagination of scientists and science fiction enthusiasts alike, and it often leads to discussions about time travel, as some theories suggest that if you could create a stable wormhole, you might be able to travel not just across space, but also through time. Imagine being able to step into a tunnel and emerge at a different point in time. perhaps witnessing historical events or even visiting the future. However, this notion is laden with paradoxes, such as the famous grandfather paradox, where a time traveler could potentially prevent their own existence by altering past events. Despite the thrilling possibilities, it's important to understand that wormholes remain purely theoretical, as no experimental evidence has yet been found to support their existence. They are a part of ongoing research in theoretical physics and cosmology, where scientists continue to explore the implications of general relativity and quantum mechanics. Some physicists are investigating whether advanced technologies could one day make it possible to create or stabilize a wormhole, while others are focused on understanding the fundamental nature of space-time itself. In the quest to understand the universe, concepts like wormholes push the boundaries of our knowledge, leading to deeper questions about the structure of reality, the nature of time, and the limits of human understanding. While we may not yet, the concept of wormholes, fascinating and complex, has intrigued scientists and curious minds alike, ever since it was first introduced in the realm of theoretical physics. The idea can be traced back to the early 20th century, when Albert Einstein, along with his colleague Nathan Rosen, published a paper in 1935 that introduced what is now known as the Einstein-Rosen bridge. This theoretical construct suggested a way to connect two separate points in space-time through a bridge, which essentially set the groundwork for what we now refer to as wormholes. Their work was rooted in the principles of general relativity, which describes gravitation as the curvature of space-time caused by mass. Although Einstein and Rosen didn't use the term wormhole, their concept inspired later scientists to explore the possibilities of these fascinating structures. In the 1980s, physicist Kip Thorne, along with Michael Morris and others, began to develop the idea further, proposing that wormholes could potentially allow for shortcuts between distant regions of the universe. They delved into the mathematical implications of traveling through such structures, discussing their stability and the exotic matter that might be necessary to keep them open, as regular matter would likely cause them to collapse. Thorne's work, particularly in collaboration with Morris, led to breakthroughs in understanding the theoretical nature of these bridges, sparking interest across the scientific community and popular culture. Their discussions raised questions about time travel, the fabric of reality, and how these ideas could fit within the universe's grand design. The concept of wormholes has since permeated science fiction, capturing the imaginations of writers and filmmakers as it presents a tantalizing glimpse into the possibilities of interstellar travel and the mysteries of the cosmos. In essence, the journey of wormhole theory reflects the collaborative nature of scientific inquiry, where ideas evolve through the contributions of many brilliant minds, highlighting how the quest for knowledge about the universe continues to inspire wonder and curiosity about what lies beyond our current understanding of space and time. Wormholes, often described as shortcuts through the fabric of space and time, have sparked the imagination of scientists and enthusiasts alike, leading to a rich array of theories about their nature and types. The most well-known type is the Einstein-Rosen bridge, which emerges from the equations of general relativity, suggesting that these bridges connect two separate points in space and time, forming a tunnel-like structure. This concept opens up fascinating possibilities, such as traveling vast distances in the universe almost instantaneously. Another intriguing type is the traversable wormhole, theorized by physicists Kip Thorne and Michael Morris, which allows for safe passage for objects and even humans. This type would need to be stabilized by exotic matter, a substance with negative energy density, which has not yet been discovered, making its existence purely theoretical for now. Additionally, there are also wormholes that could be classified based on their shape, such as the Schwarzschild wormhole, which is a non-traversable solution to Einstein's equations, suggesting a connection between two black holes. Then there are the rotating or Kerr wormholes, which allow for a different kind of passage, potentially connecting different points in time as well as space, creating a more complex structure that could bend the very notion of time travel. The idea of multiple or branching wormholes has also been explored, where one could potentially find various paths leading to different destinations, reflecting a multiverse concept, where each decision creates a diverging path in the fabric of reality. Furthermore, there are speculative ideas about wormholes being created in higher dimensional spaces, which would involve dimensions beyond the three we experience daily, suggesting that a wormhole could exist in a multi-dimensional universe. These theories, while fascinating, remain speculative and far from being proven or observed, as the conditions required to create or maintain a wormhole are still unknown. The study of wormholes, while theoretical, invites us to consider the very nature of our universe, pushing the boundaries of our understanding of physics and reality itself, making it a topic of great interest, not only in scientific communities, but also in popular culture, where stories of time travel and interstellar journeys capture the imagination of many. Wormholes, often described as shortcuts through space and time, have a fascinating connection to the theory of general relativity, which was proposed by Albert Einstein in the early 20th century. General relativity revolutionized our understanding of gravity, depicting it not as a simple force, but as the curvature of space-time caused by mass. This means that massive objects like planets and stars bend the fabric of space and time around them, creating a sort of well that other objects fall into, which we perceive as gravitational attraction. Within this framework, wormholes emerge as solutions to the equations that describe how matter and energy influence space-time. The idea of a wormhole, also known as an Einstein-Rosen bridge, arises when we explore the geometric properties of space-time. Essentially, a wormhole is theorized to connect two separate points in space-time, potentially allowing for instantaneous travel between them. Imagine the universe as a piece of paper. If you fold that paper so that 2 points touch, a straight line drawn between them represents a wormhole, offering a shortcut rather than traveling along the surface. This concept, while captivating, raises numerous questions about stability and traversability. For instance, it is believed that a wormhole could be held open by exotic matter, which possesses negative energy density, a type of matter that has not yet been discovered in nature. Moreover, the implications of traversable wormholes extend beyond mere travel. They also touch upon the nature of time and causality. If someone were to travel through a wormhole, they might find themselves not just in another location, but potentially in another time as well. This leads to intriguing paradoxes, such as the famous grandfather paradox, where a time traveler could inadvertently prevent their own existence. The mathematics involved in wormholes and their relationship to general relativity is complex, often requiring advanced concepts in theoretical physics. Yet the allure of these cosmic phenomena continues to inspire scientists and dreamers alike. In conclusion, while wormholes remain theoretical constructs, their connection to general relativity showcases the depth of our understanding of the universe, illustrating how mass and energy can shape the very fabric of reality. As research continues into the nature of space-time, the potential for new discoveries related to wormholes could reveal much about the fundamental workings of our universe, inviting both skepticism and wonder about what lies beyond our current knowledge. The Einstein-Rosen bridge, often referred to as a wormhole, is a fascinating concept in the realm of theoretical physics, particularly in the context of general relativity. It was first proposed by Albert Einstein and his colleague Nathan Rosen in a paper published in 1935. Essentially, they introduced this idea to describe a hypothetical tunnel-like structure that connects two separate points in space-time, meaning that it could potentially allow for instantaneous travel between these 2 points, which could be light years apart in the universe. This concept is deeply rooted in the equations of general relativity, which describe how gravity affects the fabric of space-time. The idea of the Einstein-Rosen bridge suggests that our universe might not be a simple, flat expanse, but rather a complex, multi-dimensional landscape where shortcuts could exist. Imagine being able to step through a portal, traversing vast distances in the blink of an eye. A notion that has captured the imagination of scientists and science fiction enthusiasts alike. However, it's crucial to understand that wormholes, including the Einstein-Rosen bridge, are purely theoretical constructs at this stage, meaning that while they are mathematically plausible, there has been no empirical evidence to confirm their existence in reality. In the realm of wormholes, there are different types that scientists theorize about. The Einstein-Rosen bridge is classified as a traversable wormhole, which would allow matter to pass through it, but it also faces significant challenges, particularly regarding stability. Theoretical physicists like Kip Thorne and others have explored the possibility of keeping a wormhole open by using exotic matter, which would have negative energy density, a concept that remains highly speculative and has yet to be realized in practice. The connection between Einstein-Rosen bridges and the broader category of wormholes lies in their shared foundation, in the theory of relativity, both exploring the implications of bending and warping space-time. These bridges symbolize a potential pathway to understanding the universe's mysteries, including the nature of black holes and the fabric of reality itself. While the idea of traveling through a wormhole might seem like something out of a science fiction novel, it prompts critical questions about the nature of time, space, and the universe. Questions that physicists continue to investigate in hopes of unraveling the complexities of our cosmos. So as you ponder the vastness of our universe, consider the possibilities that the Einstein-Rosen bridge opens up, not just for travel, but for our understanding of fundamental physics, inviting us wormholes, those fascinating structures that capture the imagination of scientists and science fiction enthusiasts alike, are described using several key mathematical equations, primarily rooted in the field of general relativity, which was formulated by Albert Einstein. At the heart of these equations is the Einstein field equation, which expresses how matter and energy in the universe influence the curvature of space-time. The equation is often written as GMN equals 8p GTMN, where GMN represents the Einstein tensor encapsulating the curvature of space-time, while TMN is the stress-energy tensor, which describes the distribution of matter and energy. This relationship highlights how gravity is not just a force, but a consequence of space-time geometry. When exploring the concept of wormholes, one of the most famous solutions to the Einstein field equations is the Schwarzschild solution, which describes black holes. But wormholes can be understood through the work of physicists Kip Thorne and others who introduced the concept of traversable wormholes. The most notable example is the Morris-Thorne wormhole, which is expressed by a specific metric that allows for a shortcut through space-time. This metric can be represented as ds2 equals minus e to the power of 2 pht2 plus wr2 slash rpr slash r plus r2 double 2 plus sin second dfph2, where pr is the redshift function and br is the shape function defining the geometry of the wormhole. Additionally, the condition for a traversable wormhole involves satisfying certain energy conditions which can be expressed mathematically. One crucial aspect is the requirement for exotic matter, which has negative energy density, allowing the wormhole to remain stable and open. The equation that often comes into play here is the energy condition, which can be described as T minimum less than 0 for some time-like vector, indicating that the energy density must be negative in specific regions of the wormhole. Moreover, the concept of the Einstein-Rosen bridge, another type of wormhole, emerges from the Einstein field equations, suggesting a connection between two black holes, creating a bridge-like structure in the fabric of space-time. This idea is encapsulated in another mathematical expression illustrating the connection between two different points in space and time. Although these equations provide a theoretical framework for understanding wormholes, it's important to note that, as of now, they remain a speculative concept with no experimental evidence. Wormholes, fascinating theoretical constructs in the realm of physics, are often described as shortcuts through space-time, connecting two distant points in the universe, or even different universes, in a way that could allow for faster-than-light travel. The concept arises from Einstein's theory of general relativity, which suggests that massive objects like stars and planets warp the fabric of space-time around them. Imagine space-time as a two-dimensional sheet, and when you place a heavy object on it, the sheet curves around the object, creating a dip. Now, if you could fold that sheet in such a way that 2 points touch, a wormhole could theoretically exist, creating a tunnel-like structure connecting those 2 points. There are two main types of wormholes discussed in physics: traversable wormholes and non-traversable wormholes. A traversal wormhole would allow for matter, such as a spacecraft, to pass through it safely, whereas a non-traversable wormhole would collapse before anything could cross. The idea of a traversable wormhole often leads to speculation about time travel, as one end of the wormhole could be moved to a different point in time, theoretically allowing someone to enter one end and exit at a different moment in time. However, the existence of wormholes remains purely theoretical, with no empirical evidence to support their existence as of now. Additionally, there are significant challenges associated with them, one of which is the requirement of exotic matter. This hypothetical form of matter would possess negative energy density, which is essential to keep the wormhole open against the pull of gravity. Without this exotic matter, a wormhole would likely collapse under its own weight. The mathematics behind wormholes often involves complex equations and concepts, including the Einstein-Rosen bridge, which is a type of wormhole proposed by Einstein and his colleague Nathan Rosen. They suggested that these bridges connect a black hole with a white hole, a theoretical entity that ejects matter instead of absorbing it. While intriguing, many scientists remain skeptical about the practicality of these constructs, as the conditions required for their existence are extreme and not found in our observable universe. In popular culture, wormholes have captured the imagination of many, appearing in science fiction stories, movies, and television shows, which often depict them as portals to distant galaxies or different times. However, while the science behind wormholes is grounded in theoretical physics, the practicality of traveling through them raises numerous questions and challenges that humanity has. Originally traversable wormholes are fascinating concepts that arise from the realms of theoretical physics, particularly within the framework of general relativity, which was formulated by Albert Einstein. To understand the conditions under which a traversable wormhole might exist, we first need to consider what a wormhole actually is. Essentially, a wormhole is a hypothetical tunnel-like structure that connects two separate points in space-time, potentially allowing for shortcuts across vast distances in the universe, or even between different times. For a wormhole to be traversable, meaning that it can be safely crossed by matter, certain conditions must be met, which involve complex relationships between energy, gravity, and the geometry of space-time. One of the key requirements for a traversable wormhole is the presence of exotic matter. Exotic matter is a theoretical form of matter that has negative energy density, which is quite different from the normal matter that we encounter every day. In simple terms, while ordinary matter has positive mass and energy, resulting in attractive gravitational forces, exotic matter would have the opposite effect, enabling it to counteract the gravitational forces that would normally collapse a wormhole. This negative energy density is essential because without it, a wormhole would likely pinch off and become non-functional almost instantaneously after forming. Moreover, the structure of a traversable wormhole must be stable, which involves specific geometric configurations. The most studied type of traversable wormhole is the Morris-Thorne wormhole, proposed in 1988 by physicists Kip Thorne and Michael Morris. This model suggests that the throat of the wormhole, which is the narrowest part that would allow for passage, must be wide enough to prevent tidal forces from tearing apart any traveler attempting to cross it. This means that the geometry must be carefully balanced to ensure that the curvature of space-time does not become overwhelming at any point during the traversal. Additionally, there are implications associated with the nature of time within a traversable wormhole. The concept of traversing a wormhole could potentially allow for time travel, raising intriguing questions about causality and the structure of the universe. Such possibilities lead to paradoxes, where one could affect events in the past, creating loops that challenge our understanding of time. To address these issues, some theories propose the need for cosmic censorship, which would prevent certain types of time travel from occurring and ensure that the fundamental laws of physics remain intact. In practical terms, the actual existence of traversable wormholes remains purely theoretical, as exotic matter holds a fascinating role in the theoretical framework of wormholes, which are often described as shortcuts through space and time, connecting distant points in the universe. To understand its significance, we must first recognize that wormholes, as proposed by physicists, are solutions to Einstein's equations of general relativity, suggesting that it is possible for the fabric of space-time to curve in such a way that two separate points can be joined. However, these theoretical constructs present unique challenges, particularly when it comes to stability and traversability. This is where exotic matter comes into play. Unlike ordinary matter, which has positive energy density and thus tends to curve space-time in ways that make it attractive, exotic matter is theorized to possess negative energy density. This peculiar property implies that it could counteract the gravitational forces that would otherwise cause a wormhole to collapse under its own weight. The significance of exotic matter is particularly emphasized in discussions of traversable wormholes, which are the kind that could, in theory, allow for safe travel between 2 points in space-time. Without exotic matter, the gravitational pull surrounding a wormhole's throat would be so strong that it would crush anything attempting to pass through. Thus, the presence of exotic matter would create a repulsive gravitational effect, keeping the wormhole open and stable. Some scientists speculate that this type of matter could exist in certain extreme environments, such as near black holes or within the context of quantum field theories, though it has yet to be observed or confirmed within our current understanding of physics. Additionally, the concept of exotic matter is closely related to the idea of vacuum energy, which is derived from quantum mechanics. This vacuum energy is thought to contribute to the overall energy density of space, and in certain theories, it could be harnessed or manipulated to create regions of negative energy density. This leads to intriguing possibilities, such as the potential for advanced civilizations to manipulate exotic matter for space travel or communication across vast distances. However, the implications of such technology would also raise ethical and philosophical questions, particularly relating to the nature of time, causality, and the potential consequences of manipulating the very fabric of reality. In the realm of theoretical physics, the quest for understanding exotic matter not only pushes the boundaries of our knowledge about wormholes, but also challenges our perceptions of the universe itself. While these ideas are still largely speculative, they open avenues for future research and exploration, inviting both scientists and enthusiasts alike to ponder the mysteries of our cosmos. The pursuit of this in the fascinating realm of theoretical physics, the concept of wormholes captures the imagination of many, offering a glimpse into the possibilities of faster-than-light travel and shortcuts through the fabric of space-time. Now, when we delve into the idea of negative energy density, things become even more intriguing. Negative energy density is a concept that arises in certain theories of physics particularly in the context of general relativity and quantum field theory. It refers to a situation where the energy density in a region of space is less than that of the vacuum energy, which is usually considered to be a baseline energy level present everywhere in the universe. If we consider a wormhole, which is essentially a tunnel-like structure that connects two separate points in space-time, the presence of negative energy density could play a crucial role. Theoretical physicists have proposed that to create and stabilize a traversable wormhole, one would need to use exotic matter, which possesses negative energy density, to counteract the gravitational forces that would otherwise cause the wormhole to collapse. This exotic matter would create a sort of repulsive gravitational effect, allowing the wormhole to remain open and passable rather than pinching shut. In more detail, when negative energy density is present, it can lead to a variety of unusual effects, such as allowing for the manipulation of space-time geometries. This manipulation could, in theory, help maintain the structure of a wormhole, preventing it from closing under the immense gravitational pull that would otherwise act on it. In essence, negative energy density acts like a balancing force, countering the attractive forces of gravity, enabling the wormhole to function as a potential conduit through which matter or information could travel. However, the existence of such negative energy density is still a subject of intense debate and research within the scientific community. Some researchers have pointed out that while certain phenomena, such as the Casimir effect, can produce local regions of negative energy density, creating a stable and macroscopic region of negative energy density required for a wormhole is still beyond our current technological and theoretical capabilities. Furthermore, the implications of utilizing negative energy density raise numerous questions about causality, time travel, and the fundamental nature of our universe. In summary, while the idea of negative energy density offers a tantalizing possibility for the existence and stability of wormholes, it remains largely theoretical, and much work is needed to fully understand its implications and whether it could ever be harnessed in a practical sense. The interplay between negative energy and stabilizing a wormhole for practical use presents a multitude of challenges, primarily rooted in our current understanding of physics and the fundamental forces at play in the universe. First, one of the most significant issues is the need for negative energy density, which is essential to keep a wormhole open. This means we need to find or create a form of exotic matter which possesses properties unlike anything we've observed. While theoretical models suggest that such matter could exist, we have yet to discover it in any significant quantity, making this a major barrier to practical wormhole stabilization. Additionally, the mathematics behind wormhole physics, as described by general relativity, indicates that even if we could create a wormhole, it would be incredibly unstable, prone to collapse under its own gravitational forces or when any mass attempts to pass through it. Moreover, the intense gravitational field surrounding a wormhole could pose significant risks. An object traveling through a wormhole might experience extreme tidal forces, leading to spaghettification, a term describing how objects are stretched and compressed in a strong gravitational field, potentially destroying anything that dares to traverse it. Furthermore, there are concerns regarding the information paradox, a concept that arises from the intersection of quantum mechanics and general relativity, which questions whether information is lost when entering a black hole or, by extension, a wormhole. The implications of this paradox could complicate the understanding and utilization of wormholes for practical purposes, as we would need to ensure that information remains intact and retrievable. In addition to these theoretical challenges, there are also engineering hurdles to consider. Even if we were to devise a method for creating a stable wormhole, the technology required to manipulate such a phenomenon would be far beyond our current capabilities. The energy requirements to maintain a wormhole open, let alone construct one, could be astronomical, possibly necessitating resources and energy sources we have not yet imagined. This leads to further questions about the sustainability and practicality of such an endeavor. How would we harness the necessary energy, and what technologies would be required to control and navigate a wormhole safely? Lastly, ethical considerations also come into play. The potential for using wormholes to traverse vast distances could lead to significant implications for space travel, exploration, and even colonization of other planets. This raises questions about the impact on existing ecosystems, potential contamination of extraterrestrial environments, and the responsibilities we hold as we venture into the cosmos. All these factors combine to create a complex web of challenges that scientists theorize that wormholes, fascinating structures in the fabric of space-time, could be created through the manipulation of gravity and exotic matter. The concept of a wormhole, often depicted in science fiction, refers to a tunnel-like connection between two separate points in the universe, potentially allowing for instantaneous travel across vast distances. According to the general theory of relativity proposed by Albert Einstein, massive objects like stars and planets warp space-time around them. This warping creates gravitational fields, which can lead to the hypothesized formation of wormholes. One prevailing theory suggests that if a sufficiently massive object were to collapse into a black hole, it could create a bridge to another point in space-time. However, to keep a wormhole stable and traversable, scientists believe that exotic matter, which possesses negative energy density, would be necessary. This exotic matter could counteract the gravitational forces that would otherwise cause the wormhole to collapse. Researchers have speculated about the existence of such exotic matter, although it has yet to be discovered or created in laboratories. Moreover, some physicists propose that wormholes could be generated through quantum fluctuations, where tiny temporary wormholes might appear and disappear at the quantum level, as suggested by theories in quantum gravity. These fluctuations might allow for microscopic wormholes, which, if harnessed, could be expanded to a scale that would allow for human travel. In addition to these theories, there's ongoing research into various models of the universe, such as string theory, which posits that the fundamental building blocks of the universe are not point-like particles, but rather one-dimensional strings. Some string theorists suggest that these strings could form complex structures that might lead to the creation of wormholes under certain conditions. While still highly speculative, these ideas highlight the complex interplay between gravity, quantum mechanics, and the fundamental structure of the universe. Scientists continue to explore these theories, hoping to find empirical evidence that could support the existence of wormholes, ultimately expanding our understanding of the cosmos and the possibilities of time and space travel. As research advances, it remains a captivating area of study in theoretical physics, sparking curiosity and imagination about the nature of our universe. Quantum gravity plays a fascinating role in our understanding of wormholes, which are theoretical passages through space-time, potentially connecting distant points in the universe or even different universes altogether. To grasp how quantum gravity fits into this picture, we first need to consider that traditional gravity, as described by Einstein's general relativity, operates on a large scale, explaining how massive objects like planets and stars warp the fabric of space-time around them. However, at the tiniest scales, the behaviors of particles and forces are governed by quantum mechanics, which introduces a level of uncertainty and complexity that traditional physics struggles to reconcile with the smooth, continuous nature of space-time described by general relativity. This is where quantum gravity comes into play. It seeks to unify these two realms, providing a framework that can describe gravitational interactions at the quantum level. One of the leading theories in this area is string theory, which suggests that the fundamental building blocks of the universe are not point-like particles, but tiny vibrating strings. In the context of wormholes, string theory offers intriguing possibilities, suggesting that the connections between different points in space-time could be formed by these strings, which could also potentially allow for the creation and stabilization of wormholes. Another approach to quantum gravity involves loop quantum gravity, which posits that space-time itself is quantized, composed of discrete units, much like how matter is made up of atoms. In this view, wormholes could be seen as fluctuations in the fabric of space-time, emerging and disappearing at the quantum level. The implications of this are profound, as they suggest that wormholes might not just be theoretical constructs, but rather they could be a natural part of the universe's quantum structure. Moreover, the concept of quantum entanglement, where particles become interconnected in ways that seem to transcend distance, adds another layer to our understanding of wormholes. Some scientists propose that entangled particles could be linked by a sort of wormhole, allowing for instantaneous communication between them, even if they are light years apart. This idea, while still speculative, opens up exciting avenues for research, as it blurs the lines between information transfer and the physical structure of the universe. As physicists continue to explore the relationship between quantum gravity and wormholes, they face numerous challenges. The mathematics involved can become incredibly complex, and many of the theories remain untested, as we currently lack the technology to observe these phenomena directly. Nonetheless, the pursuit of understanding how wormholes could fit into wormholes, a fascinating concept in the realm of theoretical physics, are often imagined as shortcuts through the fabric of space and time, allowing for potentially faster than light travel. To understand how this might work, we first need to think about the nature of space, which, while it can seem like a vast, unyielding expanse, is actually more dynamic than it appears, influenced by the presence of matter and energy. According to the theory of general relativity proposed by Albert Einstein, massive objects like stars and planets warp the space around them, creating a sort of curvature. Now picture this curving as a two-dimensional sheet being warped by a heavy ball placed in the center. If we could fold that sheet so that two distant points touch each other, we could create a shortcut or a wormhole connecting those 2 points through a tunnel-like structure. This wormhole, theoretically, could allow something or someone to enter at one end and emerge almost instantaneously at the other end, significantly reducing the travel time across vast distances in space. However, the idea of traversable wormholes comes with its own set of challenges and mysteries. For instance, maintaining the stability of a wormhole might require exotic matter, which has negative energy density, something that has yet to be discovered or created. This exotic matter could help keep the tunnel open, preventing it from collapsing under the weight of gravity, which is a significant concern since any real wormhole would likely be subject to immense gravitational forces. In addition, there are discussions among physicists about the implications of traveling through a wormhole, particularly regarding causality, the relationship between cause and effect. The potential for creating time loops or paradoxes raises interesting questions about the nature of time itself. Some theorists speculate that if wormholes could connect different points in time as well as space, it might make time travel possible, opening up a whole new realm of possibilities that stretch the limits of our understanding. Despite these intriguing theories, it's important to note that wormholes remain purely hypothetical at this stage, with no experimental evidence to support their existence. The calculations that suggest their possibility rely on complex mathematical models and assumptions that have yet to be proven in the physical world. Researchers continue to explore the implications of wormholes, as well as the fundamental laws of physics governing our universe, hoping to deepen our understanding and perhaps one day unlock the secrets of faster-than-light travel. The pursuit of knowledge in this area not only challenges our current time travel, especially through wormholes, opens up a fascinating world of possibilities, and yet also presents us with several potential paradoxes that challenge our understanding of physics and reality. One of the most famous paradoxes is the grandfather paradox, which poses the question, what would happen if you traveled back in time and accidentally prevented your grandparents from meeting? If that were to happen, then you would never be born, which raises the question of how you could have traveled back in time in the first place. This creates a loop of contradictions, making us ponder the very nature of causality and existence. Another intriguing paradox is the bootstrap paradox, which occurs when an object or piece of information is sent back in time, and it becomes the very origin of itself in the future. For instance, if a time traveler were to take a book from the future, travel back and leave it for their younger self, who then publishes it, we are left wondering who actually wrote the book. This paradox challenges our understanding of the flow of information and raises questions about originality and creativity. Additionally, there is the multiple universe hypothesis, which suggests that every time a time traveler makes a change in the past, it creates a new branch in the timeline, leading to multiple realities. If you were to go back and change a significant event, such as stopping a war, you might create an alternate universe where that event never occurred, while the original timeline still exists. This idea of branching timelines introduces complexities about identity and existence, as it suggests that there are countless versions of ourselves living out different lives across different realities. Moreover, the time dilation effect, as described by Einstein's theory of relativity, complicates matters further. When traveling at speeds close to the speed of light, time would pass differently for the traveler compared to those remaining stationary. If a person were to journey through a wormhole and return to find that many years have passed on Earth, this raises questions about the nature of time itself and whether it is absolute or relative. Lastly, the causal loop is another mind-bending concept, where events are the result of time travel, leading to a situation where an effect precedes its cause. This could mean that a traveler goes back in time to deliver a crucial piece of information that they received from their future self, thus creating a loop where the information has no clear origin. Each of these paradoxes invites us to reconsider our understanding of wormholes. Those fascinating structures in theoretical physics challenge our understanding of causality in profound ways, inviting us to rethink the very fabric of space and time. Traditionally, causality is understood as the principle where cause precedes effect, creating a timeline that is linear and predictable. However, the idea of wormholes, which are hypothetical passages through space-time, suggests that there could be shortcuts connecting distant points in the universe. This concept leads to intriguing implications, particularly when we consider the possibility of traveling through a wormhole to the past or future. Imagine stepping into a tunnel that links two separate points in space, allowing you to traverse vast distances almost instantaneously. If such a wormhole were to exist, it could allow for scenarios where events in the future somehow influence the past, creating a loop of causality that defies our conventional understanding. For instance, this raises the question of whether one could travel back in time, and if so, would it be possible to change past events? If a traveler were to prevent a significant historical event, such as the assassination of a key figure, the implications for history could be monumental, leading to paradoxes that challenge the very essence of cause and effect. Moreover, physicists like Kip Thorne have explored these ideas, suggesting that the existence of wormholes could imply a multiverse where multiple timelines coexist. In this framework, different decisions or events could lead to branching realities, where each timeline reflects a different outcome based on choices made. This challenges the idea of a single linear timeline and suggests a more complex structure to reality, where causes and effects are not as straightforward. Additionally, the concept of time travel through wormholes raises questions about determinism. The philosophical idea that every event is determined by preceding events in accordance with natural laws. If wormholes allow for backward time travel, then the deterministic view of the universe becomes complicated, as it suggests that future events could potentially alter past ones. This creates a fascinating interplay between physics and philosophy, where the implications of wormholes extend beyond mathematics and into our understanding of existence itself. In summary, wormholes serve as a powerful thought experiment, pushing the boundaries of our understanding of causality, time, and reality. They invite us to question the nature of time, exploring the possibility of multiple timelines and the impact of time travel on the universe's structure. As we continue to explore these concepts, we find ourselves at the intersection of science and philosophy, pondering the very nature of existence and wormholes, often described as shortcuts through space and time, present fascinating implications for our understanding of time itself, leading to intriguing discussions among physicists and cosmologists. Imagine, if you will, a tunnel, one that connects two distant points in the universe. And this tunnel does not just traverse space, but also time, allowing for the possibility of moving between different moments in time, not just locations. This idea stems from the theory of general relativity proposed by Albert Einstein, which suggests that massive objects can warp the fabric of space-time. Within this framework, wormholes are theorized to create bridges between various points in space-time, potentially allowing for travel to the past or the future. If wormholes exist, they may challenge our conventional understanding of causality, the principle that cause precedes effect. For instance, if one could travel through a wormhole to the past, it raises paradoxes, like the famous grandfather paradox, where a time traveler could potentially prevent their own existence by altering significant events. The implications of this question force scientists to rethink the nature of time itself, suggesting it might not be linear as we typically perceive it, but rather more fluid and interconnected, allowing for multiple timelines or realities. Moreover, the concept of time dilation, which occurs at high speeds or in strong gravitational fields, adds another layer of complexity. According to Einstein's theory, time moves slower in stronger gravitational fields, leading to scenarios where two observers, one near a massive object and the other far away, experience time differently. If wormholes were to be navigated, the traveler could encounter extreme time dilation effects, meaning that while they might experience a short journey, significantly more time could pass for someone outside the wormhole. This adds to the idea that traveling through a wormhole could not only alter spatial positions, but also lead to vastly different temporal experiences. The mathematics supporting wormholes relies heavily on theoretical constructs, such as exotic matter, which would be required to keep a wormhole open and stable. This exotic matter with negative energy density challenges our current understanding of physical substances and forces. If such matter could be harnessed, it could enable the creation of stable wormholes, making the theoretical possibility of time travel a tangible reality. However, the existence of exotic matter has not yet been proven, leaving the concept of stable wormholes and thus time travel within the realm of speculation. In the quest to understand these cosmic phenomena, scientists explored various models of wormholes. Scientists intrigued by the possibility of wormholes, those fascinating theoretical passages through space-time, have proposed several methods to test their existence, relying on advanced technology and deep understanding of physics. One approach involves studying gravitational waves, which are ripples in space-time caused by massive objects like merging black holes or neutron stars. When these events occur, they create disturbances that might reveal information about the structure of space-time, possibly indicating the presence of a wormhole. Researchers use laser interferometers such as LIGO and Virgo to detect these gravitational waves, looking for patterns that could suggest a wormhole signature. Another method involves examining the cosmic microwave background radiation, the afterglow of the Big Bang, which fills the universe. Scientists theorize that if wormholes exist, they could influence the distribution of this radiation, creating anomalies that could be detected with sensitive instruments. By analyzing the subtle fluctuations in this background radiation, scientists hope to find indirect evidence of wormholes. Additionally, there's the idea of using high-energy particle collisions, particularly those conducted in particle accelerators like the Large Hadron Collider. When particles collide at incredibly high speeds, they create conditions similar to those shortly after the Big Bang. Some physicists suggest that these conditions might allow for the creation of mini wormholes, albeit for a brief moment. By studying the outcomes of these collisions, particularly looking for unexpected results or missing energy, scientists could gain insights into the existence of wormholes. Moreover, theoretical physicists are also exploring the concept of exotic matter, which is essential for stabilizing a wormhole and allowing it to remain open. Exotic matter has negative energy density and could counteract the gravitational forces that would otherwise cause a wormhole to collapse. Experiments aimed at creating or detecting exotic matter could provide crucial clues about the feasibility of wormholes. Furthermore, scientists are delving into quantum mechanics and theories that combine with gravity, such as string theory and Luke quantum gravity. These theories propose different models of space-time that might include wormholes as part of their structure. By exploring the predictions of these theories and testing them against experimental data, researchers could potentially confirm or refute the existence of wormholes. In the realm of astrophysics, astronomers continuously observe massive celestial bodies like black holes for signs of unusual behavior that could indicate a wormhole's influence. For instance, if a black hole interacts with matter in unexpected ways, it might suggest the presence of a wormhole nearby, as these hypothetical structures. In the vast realm of astrophysics, the concept of wormholes, those fascinating theoretical passages through space-time, has captured the imagination of scientists and enthusiasts alike. To identify the presence of a wormhole, researchers would rely on a variety of observational evidence, often looking for indirect signs, since wormholes themselves may not be directly visible. One significant piece of evidence could be the gravitational effects on nearby celestial bodies. If a wormhole existed, it might warp space-time in such a way that the movement of stars, planets, or gas clouds would be affected in unusual patterns. Astronomers would meticulously observe these gravitational interactions, comparing them to the expected orbits of these objects without the influence of a wormhole. Additionally, the presence of high-energy emissions, such as X-rays or gamma rays, could suggest the existence of a wormhole. If matter were to fall into a wormhole, it might create intense radiation as it accelerates and heats up, producing detectable signals that could be picked up by our sensitive instruments here on Earth. Scientists also theorized that if a wormhole were connected to different regions of the universe, it could create a unique gravitational lensing effect. This means that light from distant stars or galaxies might be bent in unexpected ways, creating multiple images or unusual arcs, which could hint at the presence of a wormhole. Moreover, anomalies in cosmic microwave background radiation, the afterglow of the Big Bang, could potentially indicate the existence of wormholes. If a wormhole were present, it might create localized areas of distortion in this radiation, causing slight variations that would stand out against the more uniform background. Observers would analyze these patterns, looking for anything that deviates from the norm. In addition to these astrophysical signatures, the study of dark matter and dark energy could provide clues. Since wormholes would interact with gravity, understanding their influence on the distribution of dark matter might reveal unexpected concentrations or voids. If researchers were to detect strange patterns in dark matter clustering, it could lead them to consider the possibility of a wormhole impacting that area of space. Finally, the theoretical framework of quantum mechanics and general relativity suggests that the universe might allow for microscopic wormholes. potentially observable at a quantum level. Experiments in particle physics, particularly those probing the fundamental forces, could uncover anomalies that point toward the existence of these tiny wormholes, opening up a whole new realm of investigation. Through careful observation, meticulous analysis, and innovative experimentation, scientists aim. Black holes and wormholes are two fascinating concepts in the realm of astrophysics, yet they are quite different in both structure and function, sparking curiosity and intrigue among scientists and enthusiasts alike. Black holes, which are formed when massive stars collapse under their own gravity, are regions in space where the gravitational pull is so strong that nothing, not even light, can escape from them. The boundary surrounding a black hole is known as the event horizon, beyond which all paths lead inevitably into the black hole itself, making it impossible for anything that crosses this threshold to return. The interior of a black hole is shrouded in mystery, and theory suggests that at its core lies a singularity, a point of infinite density where the laws of physics as we know them cease to function. This unique structure leads to fascinating phenomena, such as gravitational waves, which are ripples in space-time caused by massive astronomical events. On the other hand, wormholes, often described as bridges in space-time, are theoretical passages that connect two separate points in the universe, potentially allowing for shortcuts between distant regions of space or even time itself. Unlike black holes, which trap matter and energy, wormholes are envisioned as tunnels through the fabric of space-time, where one end could be light years away from the other. The concept of wormholes arises from Einstein's theory of general relativity, which suggests that the fabric of space-time can be warped and manipulated under certain conditions. While black holes are well supported by observational evidence, such as the detection of gravitational waves and the imaging of the event horizon of a supermassive black hole in the galaxy M87, wormholes remain purely theoretical and have yet to be observed or proven to exist. In terms of function, black holes primarily serve as regions of extreme gravitational influence affecting nearby stars and gas clouds, often pulling them in and forming what is known as an accretion disk, where matter spirals inwards, heating up and emitting radiation. This process can lead to some of the brightest phenomena in the universe, such as quasars, which are incredibly luminous objects powered by material falling into supermassive black holes at the centers of galaxies. Wormholes, conversely, are theorized to have the potential to allow for instantaneous travel between 2 points, which raises exciting possibilities for concepts like time travel or interstellar travel, although such ideas remain in the realm of science fiction for now. The structure of a black hole is relatively straightforward. Navigating through a wormhole, a fascinating concept in theoretical physics, requires a deep understanding of general relativity and quantum mechanics, as well as a dash of imagination. Wormholes, often described as shortcuts through space-time, are hypothetical passages that connect distant parts of the universe, or even different universes altogether. One of the most discussed theoretical methods for navigating through a wormhole involves the concept of exotic matter, which refers to materials that have negative energy density. This exotic matter could theoretically stabilize a wormhole, preventing it from collapsing while allowing objects to pass through. Scientists like Kip Thorne, a renowned physicist, have explored this idea, suggesting that if we could find or create such matter, it might be possible to keep a wormhole open long enough for safe passage. Another intriguing method involves the manipulation of a wormhole's entrance and exit points. According to Einstein-Rosen bridge theory, wormholes could theoretically connect 2 different points in space-time. But the challenge lies in locating these points, which may not always be stationary. Advanced technology, perhaps involving artificial intelligence, could be used to calculate the most efficient path through wormholes, taking into account gravitational forces and other cosmic factors. Additionally, some theories propose that using high-energy particles, or lasers, to create a controlled environment around a wormhole could help facilitate travel, allowing for a safe entry and exit. Time travel is another fascinating aspect of wormhole navigation, as some theories suggest that traveling through a wormhole could allow one to move not just through space, but also through time. This introduces a host of paradoxes and complex theories, such as the grandfather paradox, where changes in the past could affect the present. To navigate through such a time-altering wormhole, one would need to have a precise understanding of the timeline involved and possibly even the ability to calculate alternate realities. Some physicists propose that the use of advanced quantum computing could aid in these calculations, providing a way to predict outcomes based on different variables, thus making navigation through a time-traveling wormhole theoretically feasible. Moreover, the concept of tunneling through a wormhole has also been discussed. This idea is based on the principles of quantum mechanics, where particles can sometimes pass through barriers that would normally be insurmountable. If applied to wormholes, it suggests that with the right conditions and technology, it might be possible to tunnel through space and time, bypassing conventional travel limitations. The concept of time travel through wormholes, while still firmly in the realm of theoretical physics, raises a host of ethical considerations that provoke fascinating debates among scientists, ethicists, and philosophers alike. One of the primary ethical dilemmas is the question of causality, which refers to the principle that cause must precede effect. If individuals could travel back in time, even the smallest change, like altering a seemingly insignificant event, could have profound and unpredictable consequences for the present and future. This possibility evokes the so-called butterfly effect, where a minor alteration in the past might lead to significant unintended changes in the timeline, potentially erasing lives or altering historical events in ways that could be harmful or unjust. Additionally, the prospect of time travel raises questions about moral responsibility. If someone travels back to a time when they could prevent a disaster or a crime, would they have an ethical obligation to intervene? Moreover, who gets to decide which events are worth changing? This leads to a risk of misuse, where individuals might exploit time travel for personal gain, to alter their own circumstances, or to inflict harm on others. The potential for creating alternate timelines also complicates the question of identity and existence, as a person could meet their past self or create a version of reality that diverges from their original experiences, leading to existential dilemmas about which version of themselves is the real one. Furthermore, the implications of time travel could extend to issues of consent and autonomy. Imagine a scenario where someone travels back in time to influence or manipulate historical figures, undermining their free will. This raises ethical questions about the rights of individuals in the past who cannot consent to interventions made by time travelers. Additionally, the ability to observe or interact with historical events could lead to voyeurism or exploitation of past traumas, treating significant moments in human history as mere spectacles for entertainment rather than respecting the gravity of those experiences. Another consideration is the societal impact of time travel technology. If such a capability were to be developed, it could be restricted to a privileged few, leading to power imbalances and inequality. Potential for a time travel elite could exacerbate existing social issues, where only the wealthy or influential could afford the means to change their past, while the less fortunate might be left to face the consequences of historical injustices without the possibility of rectification. Moreover, the environmental implications of time travel cannot be ignored. The act of traversing through time and space could have unforeseen consequences. The concept of wormholes, often depicted in science fiction as shortcuts through space and time, finds an intriguing place within the broader context of multiverse theories. In essence, wormholes are theoretical passages through space-time which could connect distant parts of the universe or even different universes altogether, suggesting a fascinating implication for multiverse theories. These theories propose that our universe, with its vast array of galaxies, stars, and planets, is just one of many that exist simultaneously, each potentially having different laws of physics, constants, and histories. When we consider wormholes in this framework, we begin to explore the possibility that they might serve as bridges between these alternate universes. Imagine a scenario where one could traverse through a wormhole to not just a different point in space, but to an entirely different universe, experiencing realities that differ in fundamental ways. Physicists like Kip Thorne, who have studied these ideas, argue that if wormholes exist, they could provide a means of travel that transcends the traditional confines of our three-dimensional experience. In this multiverse context, the existence of wormholes could imply that the fabric of reality is far more intricate and interconnected than we currently understand. Some theories even suggest that these wormholes may be created by fluctuations in quantum fields, hinting at a deeper relationship between quantum mechanics and the structure of space-time itself. Moreover, the exploration of wormholes raises questions about the nature of time. If they connect different points in time as well as space, they might allow travel not just to other universes, but also to the past or future of our own universe, further complicating the multiverse narrative. This leads to fascinating discussions about causality and the potential paradoxes that could arise from such travel, like the well-known grandfather paradox, which posits that if you were to travel back in time and change something significant, it could alter your own existence. In recent years, developments in string theory and quantum gravity have provided new frameworks for understanding wormholes and their potential role in a multiverse. These theories propose that at the smallest scales, the universe is made up of fundamental strings and branes, which could allow for the existence of wormholes as stable entities. This aligns with the idea that the multiverse is not just a theoretical concept, but may have real physical manifestations that could be explored through advanced technologies in the future. However, it is essential to note that while these ideas are exciting, they remain speculative and largely theoretical. Wormholes have captured the imagination of many, featuring prominently in various famous science fiction stories where they often serve as portals for interstellar travel, connecting distant parts of the universe and enabling characters to move across vast distances almost instantaneously. One of the most notable examples is The Forever War by Joe Haldeman, which presents wormholes as a means for soldiers to travel through time and space, with the challenges of relativistic time dilation adding layers of complexity to their journeys. Another key work is Contact by Carl Sagan, which portrays wormholes as a sophisticated means of travel, suggesting that advanced civilizations could harness such phenomena to communicate across galaxies. As the protagonist, Ellie Arroway, discovers a method to reach another star system through a wormhole, which is both scientifically intriguing and philosophically profound. In Interstellar, directed by Christopher Nolan, wormholes are depicted as natural phenomena in space, created by the gravitational forces of massive celestial bodies. The film explores the concept of a wormhole that allows space travelers to reach distant galaxies, and it delves into the implications of time, gravity, and the survival of humanity, while also grounding its scientific premise in real physics, thanks to the involvement of physicist Kip Thorne, which adds a layer of credibility to the portrayal. Similarly, in the Star Trek franchise, particularly in Star Trek Voyager, the concept of the Borg using a stable wormhole to travel vast distances is explored, emphasizing the potential dangers and wonders of such travel, as well as the ethical implications of encountering new species and civilizations. Furthermore, in The Hitchhiker's Guide to the Galaxy by Douglas Adams, Wormholes are humorously depicted as a way to travel between different parts of the universe, often resulting in chaotic and unexpected outcomes, which adds a comedic twist to the concept of space travel. The use of wormholes in this context highlights not only the absurdity, but also the unpredictable nature of traveling through such cosmic shortcuts. In Event Horizon, the narrative takes a darker turn, where a wormhole is utilized to create a gateway to another dimension, leading to horrifying consequences illustrating the potential dangers of tampering with these cosmic phenomena. In The Time Machine by H.G. Wells, while not explicitly called wormholes, the concept of time travel and the manipulation of space and time aligns closely with the idea of wormholes, suggesting that time itself can be traversed in ways that challenge our understanding. Wormholes, those fascinating theoretical passages through space-time, capture the imagination of scientists and enthusiasts alike. Serving as more than just a plot device in science fiction, they represent a potential bridge between different points in our universe and even perhaps different universes altogether. The concept of wormholes suggests that they could connect distant regions of space, allowing for shortcuts that might make interstellar travel feasible. But when we delve into the realm of parallel universes, the implications become even more intriguing. In various interpretations of quantum mechanics, particularly the many worlds interpretation, every decision or event spawns a branching of universes, leading to a multiverse composed of countless coexisting realities. In this context, wormholes could theoretically act as conduits between these parallel universes, enabling travel or communication among them, though this remains purely speculative. The mathematics behind wormholes, primarily derived from the equations of general relativity, hints at their existence, suggesting that if they do exist, they might allow for the exchange of information or even matter between these different realities, potentially resolving paradoxes associated with time travel or alternate histories. However, the stability of wormholes is a significant concern. Many physicists believe that they would require exotic matter, which has negative energy density, to remain open and traversable. Despite the challenges, this idea fuels ongoing research as scientists explore the fundamental nature of space-time and what it could mean for our understanding of reality. Moreover, the study of wormholes and their potential connection to parallel universes invites a myriad of questions about the nature of existence itself. If wormholes could link different realities, what would that mean for the concept of self? Would we encounter alternate versions of ourselves, living out different choices in parallel dimensions? This notion provokes both philosophical and scientific discourse, pushing the boundaries of our understanding and inspiring new generations of thinkers to explore the cosmos, not just as a vast expanse of stars and planets, but as a complex web of intertwined realities shaped by the very fabric of the universe. As researchers continue to investigate the implications of wormholes, they also ponder the fundamental laws that govern our universe, seeking to uncover the mysteries that lie beneath the surface of what we perceive as reality. The interplay between wormholes, parallel universes, and the fabric of space-time not only challenges our current understanding of physics, but also encourages us to imagine a universe far more complex and interconnected than we could have ever envisioned, urging us to keep questioning. Gravitational waves, which are ripples in space-time caused by some of the universe's most energetic events, such as merging black holes or neutron stars, have opened up new avenues for understanding complex concepts in theoretical physics, including wormholes. Wormholes, often depicted as shortcuts through space-time, are solutions to the equations of general relativity proposed by Albert Einstein that suggest the possibility of connecting distant parts of the universe. The relationship between gravitational waves and wormholes is mainly theoretical, as both phenomena arise from the same principles of general relativity, but they also represent different aspects of the fabric of space-time. When we observe gravitational waves, we are detecting changes in the curvature of space-time, which provides insights into the dynamics of massive objects and their interactions. These observations allow scientists to test the limits of Einstein's theory and explore extreme conditions that could potentially lead to the existence of wormholes. For example, certain models of wormholes suggest that they could emit gravitational waves, if they exist, and interact with surrounding matter. The detection of these waves could serve as indirect evidence of wormholes pushing the boundaries of our understanding of the universe. Moreover, the study of gravitational waves might help in understanding the stability of theoretical wormholes. Some types of wormholes, known as traversable wormholes, require exotic matter to remain stable, which possesses negative energy density. The behavior of gravitational waves in the vicinity of such structures could provide clues about their stability and the conditions necessary for their existence. By analyzing how gravitational waves travel through or interact with the space-time around a potential wormhole, researchers can glean important information about the properties of these fascinating cosmic structures. As gravitational wave astronomy continues to advance, the potential to explore these connections could lead to groundbreaking discoveries. The technology used to detect gravitational waves, such as the Laser Interferometer Gravitational Wave Observatory, is becoming increasingly sophisticated, allowing for a more detailed study of the universe's most extreme phenomena. If future observations reveal anomalies in the data that could be attributed to wormholes or their effects, this could revolutionize our understanding of both gravitational waves and the possibility of traversable wormholes. In essence, the interplay between gravitational waves and wormholes is a rich field of theoretical inquiry. The implications of such studies extend beyond mere curiosity, touching on fundamental questions about the nature of reality, the structure of the universe, and the potential for interstellar travel. As our technology improves and our understanding deepens, we may find ourselves on the wormholes. Fascinating structures in the fabric of space-time have captured the imagination of scientists and science fiction enthusiasts alike. Yet their feasibility remains a topic of intense debate among physicists. According to current scientific understanding, as outlined in numerous studies and articles with reputable sources such as NASA and the European Space Agency, wormholes are theoretical passages through space-time, predicted by the equations of general relativity formulated by Albert Einstein. These hypothetical tunnels could, in theory, connect distant regions of the universe, potentially allowing for shortcuts between vast distances. However, the scientific consensus emphasizes that, although they are mathematically possible, there are significant challenges that make their practical realization highly questionable. One major hurdle is the requirement of exotic matter, a form of matter with negative energy density, which is essential to keep a wormhole stable and open. Research published in journals like Physical Review D has shown that without this exotic matter, a wormhole would collapse almost instantaneously, making it impossible for anything to traverse through it. The existence of exotic matter is still purely theoretical, and no experimental evidence has yet confirmed its presence in nature. Furthermore, even if exotic matter were found, the quantities needed to stabilize a wormhole would be immense, possibly beyond our current technological capabilities. Additionally, there are questions about the safety of traveling through a wormhole, should one ever be created. The intense gravitational forces and tidal effects near the entrance of a wormhole could be catastrophic, potentially tearing apart anything that attempts to pass through. Articles in popular science publications like Scientific American highlight these dangers, suggesting that even if we could construct a wormhole, the risks involved would be daunting. Moreover, the concept of traversable wormholes raises paradoxes related to causality and time travel, which many physicists find troubling. For instance, if someone were to travel back in time through a wormhole, it could lead to situations where they could alter past events, creating inconsistencies in the timeline. This has led to discussions among theoretical physicists, with some proposing that the universe might have built-in mechanisms to prevent such paradoxes from occurring. Despite the challenges and uncertainties, research into wormholes continues to be a vibrant area of theoretical physics, with scientists exploring various models and scenarios. The ongoing exploration is fueled by a desire to understand the fundamental nature of the universe, as well as the potential implications for concepts like black holes and the fabric of space-time itself. While the consensus today suggests that wormholes remain, advancements in technology have greatly influenced our understanding of wormholes, those fascinating hypothetical passages through space-time, which in theory could connect distant parts of the universe. As scientists explore the mysteries of the cosmos, new technologies such as powerful telescopes, advanced computational models, and sophisticated particle accelerators have provided us with better tools to study the fabric of space-time and the fundamental forces that govern it. For example, the development of the Event Horizon Telescope, which captured the first image of a black hole, has opened new avenues for understanding the extreme gravitational environments where wormholes might exist. This image has not only enhanced our understanding of black holes, but also sparked discussions about the potential for wormholes to connect to those regions of space. Moreover, advancements in quantum computing allow physicists to simulate complex models of wormholes more efficiently, offering insights into their properties and behaviors under various conditions. These simulations can explore scenarios that were previously too complex to analyze, revealing how wormholes might interact with matter, energy, and even light. Additionally, by studying gravitational waves detected by observatories like LIGO and Virgo, researchers can gain information about the cosmic events that could hint at the existence of wormholes. As gravitational waves carry information about the dynamics of massive objects, they may help scientists detect anomalies that suggest the presence of these theoretical structures. Furthermore, the integration of artificial intelligence into astrophysics research has accelerated the analysis of vast amounts of astronomical data, enabling scientists to identify patterns and anomalies that could indicate the presence of wormholes or similar phenomena. AI can quickly sift through data from space missions and telescopes, flagging interesting objects or events for further study, which may lead to discoveries related to wormholes or even new theories about the universe. With each technological leap, our capacity to probe the unknown expands, allowing us to ask deeper questions about the nature of reality. In addition, the ongoing research in theoretical physics, particularly in string theory and loop quantum gravity, is being supported by technological advancements that enhance our understanding of the fundamental aspects of space and time. These theories suggest that wormholes could be more than just science fiction, proposing mechanisms through which they might actually form and exist in the universe. For example, theoretical frameworks suggest that tiny microscopic wormholes could be present at the quantum level, and as our experimental techniques improve, we might one day be able to observe these phenomena directly, potentially reshaping our understanding of the universe. In essence, the interplay of technology and theoretical physics is wormholes, often described as shortcuts through the fabric of space-time, have intrigued scientists and philosophers alike, sparking the imagination about their implications for the fate of the universe. In theory, a wormhole connects two distant points in space and time, allowing for instant travel between them. This concept challenges our traditional understanding of the universe's structure and raises profound questions about causality and the nature of reality itself. If wormholes exist, they could potentially allow for travel not just across vast distances, but also back in time, leading to scenarios that could alter the course of history. The existence of such phenomena could mean that the universe is more interconnected than we currently perceive, with the potential for alternate realities or timelines. Moreover, the implications of wormholes extend into the discussion of black holes and the ultimate fate of our universe. Some theories suggest that if a wormhole could be stabilized, It might allow matter and information to escape from black holes, which are traditionally seen as irreversible traps. This raises further questions about the nature of information in the universe and whether it can ever truly be lost. The potential for wormholes to provide escape routes from black holes could have a dramatic impact on our understanding of cosmic evolution, potentially influencing the eventual fate of galaxies and stars. Additionally, the existence of traversable wormholes might offer insights into the dark energy that is driving the accelerated expansion of the universe. If we could manipulate wormholes, we might be able to harness them to counteract the effects of dark energy, leading to new possibilities for cosmic stability or even the colonization of other galaxies. This opens up a realm of possibilities where humanity could explore and inhabit regions of the universe previously thought unreachable, fundamentally altering our place in the cosmos. However, the reality of creating or discovering such wormholes is fraught with challenges, as they would require exotic matter with negative energy density, something that has yet to be observed or understood in practical terms. This brings us back to the question of the universe's fate, as the existence of wormholes could imply a more dynamic and less deterministic universe, one where the past, present, and future are not fixed but rather fluid and flexible. As we consider the implications of wormholes, we also must ponder their impact on our understanding of time itself. If time travel were possible through wormholes, what would that mean for our perception of time? Would events be predetermined or could they be altered, leading to paradoxes that challenge our current understanding? Wormholes, fascinating structures predicted by the theory of general relativity, could potentially serve as shortcuts through space-time, making interstellar travel a more feasible concept in the future. Imagine, if you will, a tunnel connecting two distant points in the universe, allowing for faster than light travel, bypassing the vast distances that separate stars. This idea, while theoretical at the moment, captures the imagination of scientists and space enthusiasts alike, as it presents a method to traverse the cosmos that could revolutionize how we think about travel beyond our solar system. The concept of a wormhole is often discussed in the context of the Einstein-Rosen bridge, which is a specific type of wormhole that connects two separate points in space-time. And while the mathematics behind these structures is complex, it suggests the possibility of creating a stable passageway that can be used for travel. In terms of practical application, the creation of a wormhole would require conditions and materials that are still purely speculative. For instance, exotic matter with negative energy density is theorized to be necessary to stabilize a wormhole and keep it open, preventing it from collapsing under gravitational forces. This exotic matter, while a staple of science fiction, has not yet been discovered, and researchers are exploring various theories and experiments to understand if it could exist. If we were ever able to harness or create such materials, the implications for travel could be profound, allowing explorers to journey to far-off galaxies in mere moments rather than decades or centuries. Moreover, scientists are investigating the potential of quantum mechanics in relation to wormholes, as some theories suggest that the microscopic wormholes could exist on a quantum level, offering insights into the nature of space-time and the universe itself. This quantum aspect adds another layer of complexity as it raises questions about the stability, navigation, and accessibility of these wormholes. If we could learn to manipulate these tiny wormholes, it might pave the way for advances in technology that could one day lead to larger, traversable versions. However, even if we can create or find a way to stabilize wormholes, there are numerous challenges to consider. For example, the potential hazards of traveling through a wormhole, such as exposure to extreme gravitational forces or unpredictable outcomes upon exit, must be carefully analyzed. Furthermore, the ethical implications of such technology, including the potential for misuse or the impact on civilizations encountered during interstellar travel, would need to be addressed by society as a whole. In the realm of science fiction, Traveling through a wormhole, while an exciting concept, often depicted in science fiction, poses several potential dangers that are not only fascinating but also deeply rooted in theoretical physics. Firstly, one of the significant concerns relates to the stability of the wormhole itself. Wormholes are hypothetical passages through space-time that could create shortcuts between distant points in the universe. However, the formation of a stable wormhole, one that can be traversed safely, is a complex issue. Theoretical models suggest that most wormholes would be unstable, collapsing before anything could pass through them, resulting in a potentially fatal scenario for any traveler. Moreover, if a wormhole could somehow be stabilized, the intense gravitational forces present in such structures might pose a severe risk. The gravitational pull near a wormhole could be incredibly strong, leading to tidal forces that could stretch or compress an object as it approaches the event horizon, a point beyond which no information or matter can escape. This effect, sometimes referred to as spaghettification, could tear apart anything that ventured too close, including a spacecraft or a human being. Another concern is the unknown nature of the environment on the other side of a wormhole. Since wormholes connect different points in space-time, the conditions could be drastically different from those on Earth. From extreme temperatures to radiation levels that are harmful to humans, the unpredictability of what lies beyond a wormhole adds another layer of risk to any journey through one. In addition to these physical dangers, there is also the aspect of potential time dilation. Traveling through a wormhole could result in significant differences in the passage of time for the traveler compared to those remaining outside. This means that a journey through a wormhole might have unexpected consequences, such as arriving in the future or the past, which could complicate matters drastically. Furthermore, there are theoretical concerns regarding the potential creation of paradoxes, such as the famous grandfather paradox, where a traveler might inadvertently alter events in the past, leading to inconsistencies in the timeline. This raises profound questions about causality and the very fabric of reality itself, which could have implications far beyond the individual traveler. Lastly, the technology required to create or manipulate a wormhole, if it exists, is well beyond our current capabilities and understanding. The energy requirements alone may be astronomical, possibly, involving exotic matter with negative energy density, which remains purely theoretical at this stage. The risks associated with unknown technologies, combined with the challenges of navigating through wormholes, those fascinating theoretical passages through space and time offer a unique perspective on black holes and their enigmatic properties, particularly when it comes to the concept of black hole evaporation. Black holes, as we understand them, are regions of space where gravity is so strong that nothing, not even light, can escape their grasp. And they are formed from the remnants of massive stars that have undergone gravitational collapse. The idea of black hole evaporation, introduced by physicist Stephen Hawking, suggests that black holes are not entirely black. They can emit radiation, known as Hawking radiation, due to quantum effects near their event horizons. This means that over incredibly long time scales, black holes can lose mass and energy, potentially leading to their eventual evaporation. Now, when we introduce wormholes into this discussion, it becomes a bit more complex. Wormholes are often thought of as shortcuts or bridges connecting two separate points in space-time, theoretically allowing for faster than light travel or instantaneous movement between distant regions of the universe. While they remain purely theoretical constructs, the implications of wormholes on black hole evaporation present intriguing possibilities. For instance, if a wormhole connects to a black hole, one could speculate about the pathways that matter and energy might take, potentially influencing the process of black hole evaporation. Some physicists have proposed that if wormholes exist, they could create alternate routes for the energy emitted during the evaporation process. In simpler terms, instead of all the energy released by a black hole simply dissipating into the surrounding space, some of it might be funneled through a wormhole to another location in the universe. This raises questions about information loss, a critical issue in modern physics. According to the holographic principle, all the information that falls into a black hole might be preserved in some form, even if the black hole evaporates. If wormholes are involved, they could provide a mechanism for this information to escape, thereby resolving some of the paradoxes associated with black hole evaporation. Further complicating matters, some theories suggest that the existence of wormholes could imply a deeper connection between quantum mechanics and gravity, two realms of physics that have traditionally been challenging to reconcile. These connections might help us understand how black holes interact with the fabric of space-time itself and how their evaporation fits into the larger framework of our universe. While wormholes remain a speculative area of study, their potential role in black hole evaporation highlights the need for a more profound understanding of the interplay between gravity, quantum string theory, a theoretical framework in physics that aims to reconcile quantum mechanics and general relativity, plays a fascinating role in the study of wormholes, which are theoretical passages through space-time that could create shortcuts between distant regions of the universe. At its core, string theory suggests that the fundamental building blocks of the universe are not point-like particles, but rather tiny vibrating strings. These strings can vibrate at different frequencies, and their various modes of vibration correspond to different particles, including those that mediate forces in the universe. This idea leads to an expanded understanding of the universe, one where the dimensions of space-time may not be limited to the familiar three dimensions we perceive, but instead include additional dimensions that are compactified or curled up in ways we cannot easily visualize. In the context of wormholes, string theory offers a framework to explore their properties and stability. Traditional theories of gravity, based on Einstein's general relativity, suggest that wormholes could theoretically exist, but they would likely be unstable and collapse quickly before anything could pass through them. However, string theory introduces new concepts, such as extra dimensions and the behavior of strings under extreme conditions, which could potentially allow for the existence of stable wormholes. Some physicists have proposed that if the extra dimensions predicted by string theory are real, they could provide a way to keep a wormhole open, perhaps through some form of exotic matter or energy that would counteract the gravitational forces trying to close it. Moreover, string theory's incorporation of quantum mechanics allows for a different perspective on the behavior of matter and energy near a wormhole. This could lead to insights into how information is preserved or lost when passing through such a structure, which is a significant question in theoretical physics, particularly in discussions about black holes and the nature of information in the universe. The interplay between quantum mechanics and gravitational phenomena is a crucial area of research, and string theory provides a mathematical and conceptual framework for exploring these ideas. Additionally, some researchers have suggested that certain types of string theory, particularly those that involve branes, multidimensional objects within the string theory framework, might allow for the construction of wormholes that connect different regions of space or even different universes within a multiverse scenario. This opens up a plethora of possibilities for understanding not just our universe, but also the potential existence of others, all linked through these theoretical wormholes. As scientists continue to push the boundaries of our understanding of the universe, string theory remains a vital area of exploration. Scientists are continually exploring the mysteries of the universe. And one of the fascinating areas of research involves the relationship between wormholes and dark matter, two concepts that, at first glance, might seem unrelated. Wormholes, which are theoretical passages through space-time, could potentially connect distant parts of the universe, serving as shortcuts between 2 points. Dark matter, on the other hand, is an invisible substance that makes up about 27% of the universe's mass energy content, yet it does not emit, absorb, or reflect light, making it undetectable through conventional means. Instead, its presence is inferred from gravitational effects on visible matter, radiation, and the large-scale structure of the universe. The relationship between the two arises from the fundamental principles of general relativity, which describes how matter and energy warp space-time. Some scientists theorize that if wormholes do exist, they might be influenced or even created by dark matter. This is because dark matter is thought to have a unique gravitational influence which could potentially stabilize a wormhole, allowing it to remain open and traversable, unlike typical black holes which would collapse into singularities. This idea opens up intriguing possibilities, suggesting that the mysterious properties of dark matter might offer insights into the nature of space-time itself, and the existence of wormholes could provide a way to understand how dark matter interacts with the fabric of the universe. Researchers also contemplate whether dark matter could play a role in the formation of wormholes in the early universe. In theoretical models, if dark matter particles were to interact in certain ways, they might create conditions ripe for the formation of these space-time tunnels. The search for evidence of such phenomena is ongoing as scientists use advanced telescopes and particle detectors to probe deep into the cosmos, looking for signs of dark matter interactions or anomalies that could suggest the presence of wormholes. While these ideas are still largely theoretical, they represent the frontier of modern physics, where the exploration of the universe's fundamental nature may one day lead to groundbreaking discoveries. The interplay between dark matter and wormholes could also help answer key questions about the universe's evolution, structure, and ultimate fate, as scientists aim to understand how these elusive components fit into the larger cosmic puzzle. As research advances, the relationship between wormholes and dark matter may reveal even more about the mysterious forces that govern our universe, merging the realms of theoretical physics and cosmic exploration in ways we have yet to fully comprehend. While wormholes remain a fascinating theoretical concept in physics, there are several significant experiments and research programs aimed at investigating these cosmic phenomena, even though direct experimentation with wormholes is currently beyond our technological reach. Theoretical physicists have proposed various ways to explore the properties and implications of wormholes, often relying on advanced mathematical models and simulations. One of the most notable areas of research involves studying the implications of Einstein's theory of general relativity, which allows for the possibility of wormholes, also known as Einstein-Rosen bridges. Researchers are examining solutions to the equations of general relativity to understand the conditions under which wormholes might exist, as well as their stability and potential traversability. In recent years, the Laser Interferometer Gravitational Wave Observatory, commonly known as LIGO, has made groundbreaking discoveries by detecting gravitational waves resulting from cosmic events such as black hole mergers. While LIGO's primary goal is not to find wormholes, the data collected can help scientists understand the nature of space-time and may provide insights into the behavior of wormholes if they exist. Additionally, the Event Horizon Telescope, which captured the first image of a black hole's event horizon, is also contributing to our understanding of extreme gravitational environments, which could indirectly inform our understanding of wormholes. Another intriguing line of inquiry involves quantum mechanics, leading to the exploration of the relationship between wormholes and quantum entanglement. Some physicists, including the renowned theorist Juan Maldacena, have suggested that there could be a connection between wormholes and the phenomenon of entanglement, which might offer a new avenue for investigation. Researchers are conducting experiments in quantum systems, hoping to uncover evidence of this connection, which could reshape our understanding of both quantum mechanics and general relativity. Moreover, the study of cosmic inflation, which describes the rapid expansion of the universe after the Big Bang, has implications for the existence of wormholes as well. Some theories suggest that during this inflationary period, wormholes could have formed, creating shortcuts through space-time. Investigating the cosmic microwave background radiation, the afterglow of the Big Bang, could provide clues about the early universe and support or challenge the existence of primordial wormholes. Theoretical studies are also focusing on the creation of artificial wormholes, often framed in the context of speculative technologies. While this may sound like science fiction, researchers are exploring the necessary conditions for creating and maintaining a traversable wormhole, which includes the requirement for exotic matter with negative energy. Wormholes are fascinating theoretical constructs in the realm of physics, particularly in the study of space-time geometry, and they challenge our conventional understanding of the universe. To grasp their influence, it's important to first understand what a wormhole is. A wormhole, often depicted as a tunnel connecting two separate points in space-time, arises from the equations of general relativity, a theory developed by Albert Einstein. These structures suggest that rather than moving through space in a straightforward manner, it might be possible to create shortcuts connecting distant regions of the universe, allowing for instantaneous travel between them. This notion of wormholes prompts us to reconsider the very fabric of space-time itself, which is a four-dimensional continuum where the three dimensions of space are intertwined with the dimension of time. When we think about traditional space-time, we envision it as a flat plane, but the introduction of wormholes suggests a more complex geometry, one where the rules might bend to allow for these incredible shortcuts. This shift in perspective can lead to questions about the nature of gravity, how it interacts with space-time, and how it might be possible to traverse these hypothetical bridges without violating the laws of physics as we currently understand them. The study of wormholes also raises intriguing possibilities about the existence of parallel universes or alternate realities. If wormholes connect different points in space-time, could they also connect different dimensions or timelines? This idea has captured the imagination of both scientists and science fiction enthusiasts alike, as it opens the door to concepts such as time travel and the multiverse theory. While these ideas remain speculative, they push the boundaries of our understanding and challenge us to think about the universe in ways we might not have considered before. Moreover, analyzing wormholes can help physicists explore the fundamental principles of quantum mechanics and how they might interact with general relativity, which has been a long-standing challenge in theoretical physics. By studying these extreme scenarios, researchers aim to unify these two crucial theories, potentially unveiling deeper truths about the universe and its underlying structure. This pursuit of knowledge not only enriches our understanding of space-time, but also fosters technological advancements, as many principles derived from theoretical physics have led to innovative applications in various fields. In summary, wormholes serve as a gateway to exploring the complex interplay between gravity, time, and the fabric of the universe, urging us to think beyond our conventional perceptions of reality and inspiring both scientific inquiry and imaginative storytelling. Recent discoveries in the field of theoretical physics have significantly advanced our understanding of wormholes, fascinating structures that are often described as shortcuts through space and time. Researchers have long speculated about the existence and nature of wormholes, but new studies and advancements in technology are shedding light on these intriguing cosmic phenomena. One of the major breakthroughs comes from advancements in gravitational wave detection, which has allowed scientists to gather more data about the fabric of space-time. For instance, the LIGO and Virgo observatories, known for detecting gravitational waves from colliding black holes, have opened a new window into understanding the possibility of wormholes. Some physicists theorize that if wormholes exist, they could be identified by unusual gravitational wave patterns, potentially offering a way to observe them indirectly. Moreover, recent theoretical work has proposed new models of wormholes that challenge previous assumptions. For example, researchers have explored the idea of traversable wormholes, which could theoretically allow for travel from one point in the universe to another without the immense gravitational forces typically associated with black holes. These models often involve exotic matter, a hypothetical substance with negative energy density, which is thought to be necessary to keep a wormhole stable and open. While exotic matter has not yet been discovered, the exploration of its properties continues to be a vibrant area of research, with scientists examining the implications of quantum mechanics on wormhole stability. In addition, advances in quantum field theory and string theory have provided deeper insights into the nature of space-time. The holographic principle, a concept that suggests our three-dimensional universe may be a projection of information stored on a two-dimensional surface, could have implications for our understanding of wormholes. This principle has led to new ways of thinking about how wormholes might connect different regions of the universe, or even different universes entirely, challenging traditional notions of space and time. Furthermore, the study of black holes continues to play a crucial role in our understanding of wormholes. The relationship between black holes and wormholes has been a topic of interest, especially in the context of the information paradox, which concerns how information is preserved in black holes. Recent proposals suggest that the information might not be lost, but rather encoded in the connections between wormholes, indicating a more complex interplay between these phenomena than previously thought. As researchers continue to explore these ideas, they're also utilizing advanced computer simulations and mathematical models to visualize and predict the behavior of wormholes. These simulations help scientists test their theories against the laws of physics, providing the future. Prospects for research on wormholes and time travel are incredibly intriguing as physicists and cosmologists continue to explore the boundaries of our understanding of the universe. Wormholes, which are theoretical passages through space-time, could potentially connect distant points in the universe, allowing for shortcuts across vast distances. Researchers are examining the equations of general relativity put forth by Albert Einstein to understand how these structures might exist. Some scientists propose that if wormholes could be stabilized, they might allow not only travel across space, but also travel across time, opening up possibilities that have long been the stuff of science fiction. As we delve deeper into quantum mechanics, the idea of time travel becomes even more fascinating. Quantum theory suggests that particles can exist in multiple states at once, leading to the concept of parallel universes and alternate timelines. This raises questions about the nature of reality and whether time is linear or can be navigated in different directions. Some theoretical physicists, like Kip Thorne, suggest that if we could harness the energy of a black hole or manipulate space-time, we might be able to create a stable wormhole, potentially allowing for time travel. Moreover, advancements in technology, such as improved particle accelerators and new observational tools, could provide the data needed to test these theories. The Large Hadron Collider, for instance, is already helping scientists explore fundamental particles and forces in ways that could shed light on the nature of space and time. While practical time travel, as seen in movies and books, remains far out of reach, the theoretical groundwork being laid today could pave the way for groundbreaking discoveries in the coming decades. Additionally, concepts like the many worlds interpretation of quantum mechanics suggest that every decision creates a branching universe, each with its own timeline. This leads to endless possibilities for time travel, as one might theoretically navigate through these different timelines. While many of these ideas are still speculative, they inspire ongoing research and discussions within the scientific community about the fabric of reality. As research progresses, ethical implications also arise. If time travel were possible, it could have profound effects on history and free will, raising questions about the consequences of changing past events. Scientists and Ethicists alike must grapple with these potential ramifications as they explore the nature of causality and the universe. In conclusion, while the idea of traveling through wormholes in time may seem fantastical, ongoing research in physics and cosmology continues to challenge our understanding of the universe, pushing the boundaries of what we know. Rainforests are often called the lungs of our planet, and it's not just a catchy phrase. These incredible ecosystems, teeming with life, play a crucial role in producing oxygen and absorbing carbon dioxide. Covering about 6% of Earth's surface, rainforests host more than half of the world's plant and animal species, making them a biodiversity hotspot. But did you know that the Amazon rainforest alone is home to about 390 billion trees? Each tree supports a vast number of organisms, including insects, birds, and mammals, demonstrating how interconnected life is within these lush environments. Moreover, the struggle for survival among species in the rainforest is an ongoing drama. For instance, the jaguar, a top predator, helps maintain the balance of the ecosystem by controlling the populations of other animals, which in turn supports the growth of vegetation. This balance is delicate, and any disruption such as deforestation can have cascading effects, not only affecting wildlife, but also the local climate. In addition to their role in biodiversity, rainforests also provide essential resources for human populations. Indigenous communities have lived in harmony with these forests for thousands of years, relying on them for food, shelter, and medicine. Many modern medicines, including treatments for cancer and other diseases, have been derived from rainforest plants, highlighting the importance of preserving these natural pharmacies. However, the threats rainforests face are significant, with logging, agriculture, and climate change leading to alarming rates of deforestation. Each year, an estimated 10 million hectares are lost, which is equivalent to the size of Iceland. And this loss not only endangers countless species, but also disrupts the water cycle, leading to altered rainfall patterns that can affect agriculture far beyond the forest borders. As we delve deeper into the animal life within these forests, the complexity of their relationships becomes evident. For example, the interaction between plants and their pollinators is a beautiful dance of life, where flowers depend on insects, birds, and bats to reproduce, while these animals rely on the nectar and fruit provided by the plants. This mutualistic relationship is vital, as it promotes genetic diversity, allowing both plants and animals to adapt and thrive through changing conditions. Moreover, the vibrant colors and calls of rainforest creatures, like the poison dart frog or the howler monkey, serve not only for communication but also for survival. Bright colors can warn predators, while the loud howls can establish territory, showcasing the myriad strategies